Good morning, everyone. So this is be a video that we're going to work on in terms of two parts that we're going to be covering: significant figures and density. So significant figures is something that we are going to be using for the remaining of the semester, and it's an important tool. It's how we go about counting the numbers that are present in measurements, and also it goes into understanding how you apply different operations in terms of keeping the accuracy consistent in an experiment. So when we talk about significant figures, all right, what it is retaining the accuracy and precision of measurements that are made during the lab, during an experiment. And so what we had to do, there are several rules that we're going to pay attention to. But the first thing is that we are going to have a set of rules for counting zeros. So how do you count a significant figure? What exactly does a significant figure look like? Well, we make many measurements. So, for example, if we were going to the lab and we measure a mass, and the mass was, let's say, 5.05 grams, and then we measure a volume, and the volume was 45.6 milliliters. These numbers that you're seeing here, that you're observing, that you're writing down, represent the accuracy and precision for the tools that you're using during the experiment. So the first thing that you have to be able to do is you have to be able to understand what are the rules for counting zeros, and specifically counting significant figures. And so the first thing is that all whole numbers are significant, meaning that they are going to be counted. So as we look at this example here, so there's two examples up here, but the next, the one that says 45.6, so this number 45.6 has three significant figures because all of the digits count, because they're all significant, they're all whole numbers. So anytime you have a number, it doesn't matter what it has to be. It could be 111, it could be 123, 5,632. So all these are just examples of things that would apply to this first number. So, you know, counting the numbers, there are three sig figs here, there are three sig figs here, and then this one has four significant figures for it. All right, so that's the first rule when counting. The second rule is all sandwiched zeros are significant, meaning that they are going to count. So again, the rules of zero is really paying attention to how that zero lies within the number itself, so that way we can pay attention to whether it's actually significant and would be counted or not. So let's go back to the first example here. So we have 5.05. So this zero is in between two whole numbers. So anytime you have a zero in between a whole number, and two whole numbers in this example, you're going to have that zero be counted as a sig fig. So in this one, you have 5.05, so that is three sig figs. Now, if I have another number, say 1001, well, notice that the zeros are in between the two ones, so they are themselves going to count. So that would be representing four sig figs there. So those are the first two rules here, all right? Now, as we move forward here, we're going to look at a couple more rules, but we have to pay attention to a very small detail, and that's the decimal place. So rule 3 is all trailing zeros will only be significant if a decimal place is present. Okay? So that's one rule. Another rule is that all leading zeros are not significant as they are only placeholders. Okay, so that's rule number 4. And then the 5th rule, and I'm kind of just putting all these out at one time because we're going to apply them in just a second. So the 5th rule is that if a decimal place is present, then all zeros trailing are significant. Okay? So those are the next 3 rules. And you know, when we start to apply this, the more you do it, the better you're going to get at it. So as we look at some examples here, so I'm just going to put up some numbers here. Okay, so we have 4 examples here, A, B, C, and D. And all 4 of these are going to be an application to those rules that we're talking about. So in the first one, in letter A here, you have 0.000501. Now, the zeros in front are leading zeros, so I'm just going to kind of underline this. These are leading zeros. So they don't count. Again, those zeros are only placeholders. They don't matter. All right, so you don't need to worry about counting them. So what is going to be counted are the 5, 0, and 1. Now this goes back to the fact that you have zeros in between, it's sandwiched, and then these 3 are significant. So this would be 3 sig figs. All right. Now, so that's letter A. Now looking at letter B, you have 1,000. Well, there's not a decimal place present. So the only thing that is going to count is going to be the 1. So this would be 1 sig fig. Now, if you look at letter C, there's a difference there. So they're the same exact number, but the difference is that you have this decimal place here. And this decimal place makes all the world difference when it counts to zeros that are to the right of the whole number. So notice that these zeros are to the right of this whole number. So this one would be 4 sig figs. All right. So let's go back to understanding and talking about the rules of zeros. So if you go into a bank and you want to deposit a check, you do not write a check to, so let's say you're depositing a $100 check. You don't go in there and you put a 0 on the front of the money, the deposit slip. You don't put a 0 in front of the 1. Why? Because the 0 doesn't matter. It's not necessary. So we don't put zeros in front. Remember that zeros in front are there as placeholders. We don't need this 0 here. Now, if we take a number like this, so let's say we take a number like this. Now, these zeros are in the front. They mean something, but we just still don't count them. The only number that does count is the 1. So this would be 1 sig fig, whereas this one here, well, this one's different because now we have the decimal place and the zeros are to the right. So the trailing zeros, which this is trailing and this is leading, all right? So the trailing zeros don't count, or the trailing zeros do count, but the leading zeros do not count. So we're going to count all these zeros, including the 1 here. So this would be an example of 5 sig figs, all right? So that would be an example there of where the zeros do count. And remember that the thing that makes them count is the decimal place. Now looking at the last example here, letter D, so we can see that this one has some leading zeros, which they don't count, so we're just going to cross them off. It doesn't matter. But what does count is everything that's afterwards. And that's because there is a decimal place. This decimal place makes the zeros to the right count. Now, we know that the 5, 0, 1 are going to count because we've already saw that up there. But it's that 0 that's on the right side that makes the difference here. And so this would be an example of 4 sig figs. And that's just because your zero is to the right of the first whole number, plus the fact that it has a decimal place as well. So remember, the takeaway from this, so you need to understand the rules for how to count the significant figures, including the zeros, all right? The zeros are going to make a huge difference in terms of how you go about calculating your final answers when we are doing future calculations. So now, going along with the calculations part, all we've done here is really reference to how we go about counting significant figures. So there are two rules that you have to pay attention to when working a calculation involving numbers. Again, all these numbers are going to be either provided to you, that's one. That would be like a question you'd see on a quiz or a test or a worksheet. But if you're working in a lab, you'd measure these numbers. So keep that in the back of your head as we're going through this. So now in terms of calculating, there are two sets of rules, all right? So calculations, the first set of rules deals with addition and subtraction. All right, so what this rule says is that you record to the least precise measurement. All right. And we're going to come back to that. So least precise means that you are recording to the least number of decimal places. And that could be a multitude of different ways of looking at it, and that depends on what you're measuring at that point in time. Rule number 2 involves multiplication and division. In this rule, it states that you record to the least number of sig figs. All right? And this goes back to counting sig figs. Right, so this goes back to the rules that we just talked about in the beginning here. It goes back to understanding that. Now, so as far as the addition and subtraction is concerned, we can do something very, very simple. And in fact, that's what we're going to do. I'm not going to do many examples because this is something you're going to apply over time, and you'll see more examples as you come across them. So let's say we measure 10 milliliters out of a graduated cylinder, and then we measure 10.00 milliliters out of a burette, and we combine them together. So the combining of them would be simply just add them together. So now you end up with 20.00 milliliters. Okay, so 10 plus 10 is 20, right? But that's easy. So doing the math is not a big deal, because all you have to do is take your calculator and add it together or multiply whatever the case is. So what we have to pay attention to is the fact of what operation we're doing. So whether we're doing addition, subtraction, or multiplication, division. This one is we're doing the addition, and so we record to the least precise measurement. So when I look at this measurement up here, what I notice is that the measurement has 10.0, so the first measurement goes to only one decimal place, whereas the second measurement goes to 2 decimal places. And so the final answer really needs to be corrected to only 1 decimal place. So the answer would be 20.0. Again, that goes back to just basically making sure that you understand the rule that you record the least precise measurement, and that in this particular example, it's to the first decimal place. All right. Now down here, if I were to take, let's say, the same numbers, all right, but this time instead of adding them, we're going to multiply them together. All right. So we know 10 times 10 is 100. All right. So the answer is 100. But the question is, how many sig figs do you record to, or what's the rule say? So the rule says record the least number of significant figures. Now, as I look at this number, I see that the first number has 3 significant figures. Remember that the zeros are going to count because they're to the right of the first whole number, plus there is a decimal place. So you have to have that rule understood. So the same thing again here. the zeros are to the right, and then that you also have that decimal place. So there are 4 sig figs here. So the final answer needs to be recorded to the least number of significant figures, and that will be 3 significant figures. So we have 3 sig figs. Now when I look at the answer here, I see that I've written it down as 100. Okay, 100 is only one significant figure because there is no decimal place. So I can simply just put a decimal place there. Now what that does is that allows the zeros to count. So now you have a total of 3 sig figs in your final answer, and that would be your answer for this particular case. So I'm going to post a worksheet. So you'll see a worksheet that pertains to significant figures along with the discussion. So look for that worksheet. Make sure that that's something that you are practicing. It's something that you'll be utilizing in the upcoming weeks in terms of how to apply rules of significant figures and the various operations that you're going to take in. Now, the last thing I want to cover in this particular lesson is density, is how to calculate density, what density is, and so that's what we're going to do. And so density is equal to mass divided by volume. All right. So every object that we have that we come in contact with has some form of density. So in my hand I have a metal object, and this metal object, there's nothing special about it or anything. So this metal object has a little bit of red staining on it, red-orange staining. It's got a little mass to it, and in fact the mass of this object is 60.879 grams. Okay. What I did was take it to the balance, set it on the balance, and measure the mass of it. So that's the mass. So this object, every object has some mass to it. Now the next thing we're going to do is we need to figure out what the volume of this object is. We don't know what the volume is. So in order to figure out the volume, all right. So again, every object has its density, its own unique density. So a good example in comparing this. So let's say we take this piece of metal, and then we take a piece of wood, right, something, a branch that falls off a tree, and we were to take them and we put them into water. Okay. So what would happen to the piece of wood if you were to put it in the water? It would float. All right. If you take ice and you put it in the water, you know ice is going to float. So we talk about density. So densities, in just kind of referring back to water, for example, water's density is 1 gram per milliliter. So that means that for every 1 milliliter of water that you have exactly 1 gram of water that's present. That's all that's telling you. Okay. So what we're going to do is we're going to figure out how this piece of metal compares to the density of water. Now I know that if I put this in the water, it's going to sink. All right. What I want to do is figure out the volume of this. So to do this, we're going to use a graduated cylinder. All right. Now in this graduated cylinder, I already have a pre-measured amount of the liquid. In this case, this water, and so that particular amount is roughly 49 milliliters. Okay. So the V initial for this in the graduated cylinder is 49 milliliters. Now one of the things you're going to notice is that I do write the first decimal place of it. So what I want to do now is I want to figure out what the volume of this object is. In order to do that, I'm going to take this object, all right, and I'm going to place it into the graduate cylinder, and you'll see the object will increase in this volume. All right. So now the new volume inside of this is roughly 56.1. So it's 56.1 milliliters. So what I want to do is I want to figure out the volume of the solid. So what I'm going to do is I'm going to take the 56.1 and I'm going to subtract that from 49, and that's going to give me 7.1 milliliters for the object. Okay, so up here we now know what the volume of that metal object is. It's 7.1 milliliters. So now I want to calculate the density of this metal. So what I do is I take the 60.879 grams and I'm going to divide it out by the 7.1 milliliters. Okay, so we're just going to type out exactly the way you see it. This is the way you'll see it on the test as well, and quizzes and everything else. So take 60.879 and then divide it by 7.1. And what we end up with is a density equal to 8.6 grams per milliliter. All right. Now, so what I'm going to do here is I'm actually going to erase this. What I want you to see is that your calculator will give you some long number, and I'm going to stop here. And we don't want to. We do not want to include all of those numbers. What we want to do is correct for the sig figs again. So we're going to apply the rules. So this is a division operation. So the thing you're going to do is you're going to look at how many sig figs the first number has, which is 5 sig figs. And then you look at the second number, and the second number is 2 sig figs. So your final answer needs to be 2 significant figures. So what we're going to do is we're going to take this here, and we're going to round it to where it has 2 sig figs. In this particular case, it's easy because we just round it to the first decimal place. All right, so now as I compare the density of this object to the density of water, and I'm going to box this in, I would expect you to memorize the density of water because that's something that we use quite often. So I want you to make sure that that's something that you know and that you've learned. All right, so make sure you memorize that value there. It's pretty easy. So we know the density of water is 1. We now know the mass and the volume of this object, and the density of it is 8.6. Anytime you have a heavier, a more dense object, it's going to sink to the bottom. So in this case, that's why it goes to the bottom. Now, if I were to take a cork or some type of wood and place that in the water, well, wood has a lower density than water, so you would expect wood to float on top. So you go back to understanding that, the different densities of objects. So, wood, I'm going to say wood is right around 0.67 grams per milliliter. And all these are in the same units of grams per milliliter, so don't forget the units. All right, wood would be this. Lead would be on the order of 12 grams per milliliter. Gold is upwards of around 18 to 19 grams per milliliter. And it's a very dense object. That's why we are able to separate it when we pan gold. So when you compare these 3 objects to water, what we'd expect is that if we had a cylinder, all right, and you have your water present here, the water is going to be sort of in the middle. Your wood is going to be floating on the top. You're going to have your gold at the very bottom. So here's a gold bar. And then on top of that, you're going to have your lead because it's a little bit less dense than the gold. So then your water's sort of in the middle here. All right. So as we talk about density, what we need to do is pay attention to the fact that density, all it is a conversion factor going from grams to milliliters, or in this particular case, knowing the density of the object. We've talked about density of water being 1 gram per milliliter, and then we compare the densities of objects to that of water, and we can kind of get an understanding of where they lie. So if you were to want to go drop something into the bottom of the lake, you don't attach wood to it because it's going to float. All right, you would attach a solid piece of metal or whatever, gold if you want to use gold. I wouldn't use gold; it's too expensive. But you attach it to lead and it sink it to the bottom. You never have to worry about it floating again. So that's where we're going to end here. All right, this is the conversation today. So we've talked about significant figures. We've discussed the rules of how to count sig figs. We've discussed how to do the calculations, the various rules. And now we looked at density in a little bit more formal way. So again, all right, thanks for watching, everyone. Have a good one.